When an autonomous vehicle approaches a hairpin turn at speed, it is calculating thousands of distinct variables. Every millisecond of delay between processing those variables and executing a steering command pushes the tires closer to a total loss of traction. This creates the core paradox of model predictive control, or MPC. To predict exactly how a car will behave, the system model needs to be deeply complex. But the more complex a model becomes, the longer it takes to compute. The standard baseline used in the industry is the physics-based dynamic bicycle model. To keep calculations fast, it relies on strict assumptions, like assuming constant longitudinal velocity. But reality rarely matches these perfect assumptions, resulting in midterm prediction errors known as the residue. To eliminate this residue, modern engineers turn to data-driven models. They feed historical sensor data into deep neural networks to learn the exact difference between the physics model and reality. But deep learning models introduce a specific limitation. By attempting to map the entire physical environment, the resulting math is highly nonlinear and non-convex. Optimization formulas that use these models require intense, repetitive calculations. A model that calculates the perfect steering angle is useless if it takes 3 seconds to output the answer. For a vehicle requiring micro-adjustments at 1000 Hz, the car has already crashed before the processor finishes the math. This image shows the Changshu Sudoku map, the designated competition area for the Intelligent Vehicle Future Challenge. The red lines trace the exact test paths. The varied geometries, especially the erratic U-turns on the right side, force standard dynamic models to continuously navigate severe environmental uncertainties. The current gold standard for mapping these deviations is Gaussian process nonlinear MPC. It operates as a probabilistic model to predict the residue across these curves. But Gaussian process hits a mathematical breaking point. Because the model is nonlinear, it relies on a sequential quadratic programming solver. This requires pulling the complex data into the objective function iteratively. As the volume of historical data grows, the optimization calculation time balloons. A research team from Xi'an Jiaotong University developed an alternative, the Random Forest's Linear Learning-Based Model Predictive Control, or RFL-MPC. Instead of trying to calculate nonlinear global physics in real time, the RFL architecture builds a hierarchical system. It categorizes the data first, routing it into discrete, easily solvable linear models before the real-time control math even begins. To understand the bottleneck, look at the baseline math. This diagram shows the dynamic bicycle model, isolating variables like lateral position and yaw angle. When the vehicle travels through a curve, assumptions cause the predicted path to diverge from the actual physical path. A Gaussian process model attempts to map this exact physical divergence by running iterative mathematical loops. Because it checks the entire nonlinear state multiple times per time step, the predictive variance complexity scales at O iter times m squared, where m is the volume of training data. The processor chokes. To prevent the system from freezing, researchers are forced to artificially cap the training data, often limiting the Gaussian process to a tiny sample size of roughly 300 data points. Starved of historical context, the car's tracking accuracy drops. As long as the control solver is trapped in an iterative nonlinear loop, achieving high-speed precision remains mathematically difficult. The RFL architecture addresses this by separating the variables entirely. It splits the telemetry stream into 2 distinct categories. The first stream contains non-control variables, like the physical vehicle states and speed. The second stream contains the manipulated control variables, specifically the steering angle. The system uses a random forest exclusively for routing the non-control data. By checking the car's physical states against a series of decision trees, the random forest classifies the exact physical situation the vehicle is experiencing, dropping data into a specific terminal leaf. Inside that specific leaf sits a pre-calculated linear regression model. This is where the second stream arrives. The control variables drop in, plugging into the custom linear equation to instantly solve the required steering input. The random forest acts strictly as a high-speed traffic director. It fragments a complex nonlinear environment into hundreds of bite-sized, instantly solvable linear equations. This diagram shows how the output merges back to form the final predictive controller. Notice the data collection and random forests model path at the bottom.
The decision trees and the linear models inside the leaves are trained on historical data offline. During a live run, the system identifies the correct leaf, pulls the linear coefficients, and algebraically adds them to the nominal model's baseline system matrix. Because the heavy classification happens through offline routing, the combined system model running on the car's processor remains strictly linear with respect to the real-time control inputs. Maintaining strict linearity provides a specific computational advantage. The system can utilize quadratic programming, or QP, solvers. Unlike the lagging iterative loops required by a Gaussian process, a QP solver executes a streamlined, one-shot calculation. This chart shows the computing complexity. The Gaussian process curves upward steeply as training data scales. The RFL method maintains a predictive mean complexity of a flat O of 1. Because the real-time calculation is independent of the training data volume, researchers can feed the random forest millions of historical data points without adding a single millisecond of drag to the processor's runtime. The model operates deterministically, overcoming traditional latency only because the hierarchical split successfully shields the final optimization solver from nonlinear math. This chart compares experimental tracking results. By incorporating local linear models, the RFL system achieved a 16% reduction in lateral tracking error. The processing difference is severe. Gaussian process required 15.4 seconds, while RFL processed the exact same track in just 0.69 seconds. The Gaussian model struggled here because researchers were forced to cap its training set to just 300 data points to keep the calculation time from crashing the system. Its situational awareness was restricted. Operating with no such data cap, the RFL car reads the track, accessing a vast repository of offline data in milliseconds to predict its grip. By moving past global approximations and instead using machine learning to rapidly switch between local linear models, we enable real-time autonomous control that is both mathematically tractable and empirically superior.
To achieve Level 4 autonomy, a vehicle must operate entirely without human intervention within a defined set of conditions. Navigating a complex real-world environment is not a simple mathematical equation. Interpreting chaotic city streets requires the immense computational power of deep learning models for both perception and planning. But applying deep learning to a 2-ton machine traveling at highway speeds exposes a structural flaw. Neural networks are inherently probabilistic. Looking at a standard probability distribution for object detection, we can see what probabilistic actually means in a mechanical context. Instead of outputting absolute mathematical certainties, the system operates on statistical distributions. It makes educated guesses. Operating on statistical distributions creates a conflict with the core requirements for Level 4 safety certification. Certification demands rigorous, deterministic guarantees, where every output is mathematically certain. A prevailing assumption in the industry is that scaling up, building a single, massive, end-to-end neural network will eventually close the safety gap. That monolithic approach fails standard engineering requirements. A massive end-to-end model is a black box. Its internal logic cannot be mathematically validated to prove it won't fail. A certifiable Level 4 architecture requires a hybrid, modular stack. It must physically bound the probabilistic capabilities of machine learning within rigid, deterministic physical rules. Safety in autonomous systems cannot be learned by an algorithm. It must be structurally enforced by the architecture itself. The foundation of this architecture is the perception layer, beginning with sensor fusion. To process this incoming telemetry, the system relies on spatial transformers. These algorithms ingest raw, unstructured dimensional data from the sensors and begin searching for recognizable patterns. As spatial transformers identify patterns, they establish 3D bounding boxes around dense clusters of data points, marking suspected objects. Attached to each box is a hidden variable, a fluctuating confidence score dictating how sure the model actually is. A 99% confidence score sounds reliable, but that margin of error allows for a hallucination, where the system either invents a phantom obstacle or ignores a massive physical one. The perception layer does not actually see reality. It only generates statistical guesses about what might be occupying the space around it. Those statistical guesses are then passed up the architectural stack to the ML planning module.
The planner's core function is to ingest the perception layer's output and predict exactly where dynamic agents, like pedestrians, will be 3 seconds into the future. Looking at a top-down vector schematic, we track kinematic trajectories. Rather than a single route, the planner extends a multitude of potential future paths, assigning probability weights and favoring trajectories that optimize for standard traffic laws. This optimization process introduces the system's primary vulnerability, the long-tail edge case. When confronted with a sudden, novel situation entirely absent from its training data, the ML planner breaks down. Because the variables no longer match its learned distributions, it fails to optimize a safe path. Training a machine learning model to optimize for standard traffic flow does not mathematically prevent it from choosing a fatal path during moments of chaos. To solve this vulnerability, engineers build a final overarching layer, the deterministic safety envelope. This layer is explicitly separated from the modules below it. It is entirely rule-based, containing 0 machine learning, 0 probabilities, and 0 neural networks. Its raw inputs are uncompromising physical laws. It continuously calculates exact vehicle stopping distances based on real-time inertia, vehicle mass, and current tire friction coefficients. This 3D representation shows how these classical physics calculations generate an absolute spatial boundary around the vehicle. This no-go zone dynamically lengthens and shortens based on vehicle speed. The ML planner's probabilistic trajectories are fed up into this physical layer for approval. If any machine learning-generated path violates the spatial boundary, the deterministic layer immediately severs and deletes it. If a chaotic situation severs all optimal paths, the deterministic layer bypasses the ML planner, triggering a hard-coded fail-safe maneuver based purely on kinematics. True safety is achieved by caging unpredictable statistical algorithms inside unyielding physical mathematics. Observing the fully assembled hybrid architecture operating in a high-density environment reveals how these layers interact in real time. Consider a complex edge case, such as an occluded dynamic agent unexpectedly cutting directly into the vehicle's immediate braking zone. The machine learning stack reacts instantly, but its perception and planning layers spike in uncertainty, generating conflicting, erratic probabilistic paths as it struggles to classify the sudden anomaly. Before those erratic paths reach the steering column, the deterministic layer intervenes. It shears away dangerous ML hallucinations, executing a mathematically verified emergency stop. This exact interaction is the defining standard of Level 4 engineering, fail operational design. In a fail operational system, when the ML model inevitably outputs a failure or an anomaly, the physical system does not crash. It degrades gracefully to a mathematically proven safe state. Engineering perfect boundaries around imperfect networks is the mechanism that delivers absolute autonomy.